This podcast was created as a supplemental learning resource for this course. The content is based on assigned course materials, including open educational resources, textbook chapters, instructor-developed explanations, examples, and applications connected to course topics. AI tools were used to help transform course material into a conversational podcast format, including the use of AI-generated narration. The AI narration is intended to make the material more engaging, accessible, and flexible for students. However, the podcast should not replace careful reading of assigned materials, reviewing course lectures, or completing course activities. Any interpretations, examples, or explanations included in the podcast are provided for educational purposes and are the responsibility of the instructor. Students should rely on the assigned readings, course lectures, and official course materials as the primary sources for exams, assignments, and class discussions.
So imagine you're just, opening the morning paper.
Right, like normal.
Yeah, and you see this massive, bold headline. It says a polling company, it's just called 1,000 Random Citizens,
Okay.
and 230 of them declared they intend to vote for the Australian Labor Party, the ALP.
Ah, I know where this is going.
Right, so the newspaper prints it as this absolute undeniable fact. They say the ALP has a 23% primary vote. End of story, lock it in.
And people just accept that.
Exactly. But if you stop and think about that for, more than 5 seconds, a terrifying mathematical reality opens up.
It really does. It's a reality that most people intuitively ignore because, frankly, it makes navigating the world way too complicated.
Yeah.
I mean, at the time of that specific election mentioned in our source material, there were over 4.6 million enrolled voters in that region.
Wow. 4.6 million.
Right, and the polling company spoke to exactly 1,000 of them.
Which means the opinions of the other 4.6 million voters are just a total mystery.
A complete blank space.
So if we strip away our assumptions, right, and act completely strictly literal, the only factual truth we can claim with absolute mathematical certainty is that the vote for the ALP is somewhere between 0.005% and 99.83%.
Yeah, that is the raw, uncomfortable truth of the data right there.
It's so wild to hear it phrased like that.
Well, I mean, in a wildly theoretical universe, maybe only those exact 230 people vote for them, right? And the other 4.6 million vote for someone else.
Right. Or conversely, maybe literally every single person in the posters didn't call votes for the ALP. We literally don't know.
We don't, but newspapers don't print ALP votes somewhere between basically 0 and basically 100%.
No, that wouldn't sell many papers. They print 23%.
Exactly, and we just accept it.
We do. We see 230 out of 1,000, and 23% just feels right.
It feels safe.
Yeah, like if election day came and the true vote was 24%, you wouldn't even blink.
No, not at all.
If it was 37%, you'd think the pollsters lied. But what if the true vote turns out to be 29%?
That's the tricky part.
Right. Like, how surprised should you be? Is that a massive polling failure? Or is it a completely mathematically plausible outcome of talking to only 1,000 people?
And the thing is, human intuition is utterly useless at answering that question.
Totally useless.
We simply do not have the cognitive hardware to, measure the exact shape of that uncertainty.
Which is why we need help.
Exactly. That is the entire reason the field of inferential statistics exists. We have to build these powerful, rigorous mathematical tools to tell us exactly how surprised we should be by a 29% result.
And that is exactly what we are doing today. If you are listening to this deep dive right now to survive a core module in your statistics course, or, if you just have this insatiable curiosity about how we separate truth from noise, you are in the exact right place.
It's going to be a fun one.
It is. We are taking the source material you provided, which covers probability, sampling, and estimation, and we're unpacking how we use incomplete, incredibly messy, real-world data to uncover the hidden state of reality.
It is such an incredibly vital transition to make because the things we normally associate with statistics, like calculating averages, formatting spreadsheets, drawing nice little bar graphs.
Yeah, the boring stuff.
Right, that is just descriptive statistics.
The text actually calls that stamp collecting with numbers.
I love that phrase.
It might be the best academic burn I've heard all year. I mean, descriptive statistics just summarizes the data sitting right in front of you.
It's just a summary.
But inferential statistics, the stuff we're diving into today, is basically magic. Just
Right.
taking the data you actually have to make mathematically bulletproof claims about the data you don't have.
And that's where the real power is.
But before we could do any of that magic, we have to talk about probability. And honestly, reading through your sources, I was just floored to find out that statisticians essentially treat probability like a religious war.
Oh, it gets very heated.
I mean, I thought maths were just objective truth.
Well, the equations themselves are objective.
Right.
Two warring statisticians will solve the exact same equation the exact same way. The vicious disagreement is over the fundamental philosophy of what the numbers actually represent in the real world.
That is so wild to me.
But to really grasp that war, we first have to draw a hard line between probability and statistics, because they are essentially inverse operations.
Inverse, like backwards.
Yeah, think of them as working in opposite directions.
Okay, let me try to map this out based on the text. So in probability, the model of the world is known, but the actual data is unknown.
Correct.
So like, if you hand me a casino grade, perfectly fair coin, I know the model. The model is a strict 50-50 split.
Exactly. You know the rules of the system.
But the unknown data is what happens if I flip it 10 times. Well, I get 6 heads. 4. Probability tells me the likelihood of those different data outcomes based on that perfectly known model.
You've got it. Now reverse that exact process.
Okay.
In statistics, the data is known, but the model is a complete mystery.
Oh, interesting.
Right. So imagine you are standing in an alleyway and a stranger flips a coin 10 times and it lands on heads all 10 times.
Okay, that's sketchy.
Very. But that sequence of 10 heads is your known data. That's what you observed.
Right.
The unknown model is the reality of the coin itself. Is it a fair coin that just hit a bizarre, streak of luck? Or is it a weighted trick coin?
I see. So statistics gives you a framework to infer the hidden model from the visible data.
Exactly. It's the engine driving the car.
I love that. But I guess that brings us right back to the philosophical bloodbath.
It does.
If probability is the engine of statistics, what actually is it? Like if a scientist tells you there is an 80% probability of an event happening, what physical reality does that 80% actually correspond to?
Well, if that scientist is a frequentist, they will offer a very rigid physical definition.
Okay, the frequentists, they were a big deal, right?
Huge. The frequentist ideology dominated the 20th century. To them, probability is nothing more than a long-run frequency.
A long-run frequency.
Yes. It is a physical property of the universe that only reveals itself over time.
So tying this back to the coin flip, the text walks through a computer simulation of this.
It does.
If you start flipping a coin, the early proportions are going to bounce around wildly.
Right.
Like first flip is tails, so you're at 0% heads.
Right.
Next is heads, now you're at 50%. Next is heads, now 67%. It looks like total chaos.
Just noise.
But the frequentist argues that as the number of flips your n stretches out toward infinity, that wild bouncing will dampen down and eventually lock in precisely at 50%.
That's their core belief. For the frequentist, probability only exists if you can repeat the experiment infinitely.
So it's completely objective.
Completely. It removes human opinion entirely. The probability is an objective, mechanical truth rooted in the physical world.
I mean, I definitely understand the appeal of that objectivity, but I have a massive problem with it, and so does the text.
Let's hear it.
Infinity is a mathematical concept. It's not a physical reality.
Very true.
If I sit at a table and physically flip a quarter millions of times, the metal is going to degrade. The oils on my thumb will literally alter the weight of the coin.
The physical object changes?
Exactly.
Yeah.
Eventually, the coin will disintegrate into dust. An infinite physical sequence is literally impossible.
A completely valid critique. The frequentist requires a hypothetical universe that simply cannot exist in reality.
And it completely falls apart for single events, too.
Oh, absolutely.
If a meteorologist goes on the nightly news and says, there is a 60% chance of rain in London on November 2nd, 2048, every person watching understands what that means.
Intuitively, yes.
But November 2nd, 2048 only happens one time. The universe does not reboot and replay that specific Tuesday a million times to tally up how often it rains.
It does not.
So how can a frequentist even use the word probability there?
They struggle with it, honestly. A strict frequentist has to do some severe philosophical gymnastics to make that work.
Like what?
Well, they might say, out of all the historical days where we observed this specific atmospheric pressure and humidity, it rained 60% of the time.
Oh, so they create a fake category.
Exactly. They have to build an artificial reference class. It feels clunky.
Clunky.
And that clunkiness is exactly what gave rise to the great alternative, the Bayesian view.
Ah, the subjectivists.
Yes. The Bayesians define probability in a radically different way. To them, probability is not a physical property of a coin or the weather or a die.
What is it then?
Probability is the degree of belief that a rational, intelligent agent assigns to an event based on the information they currently have.
Okay, let's unpack this, because the text uses this bizarre but honestly really helpful rational gambling thought experiment to explain it.
It's a great example.
So imagine a robot soccer match. Arduino Arsenal versus C Milan.
Classic matchup.
Truly, if I'm a Bayesian and I say Arduino Arsenal has an 80% chance of winning, I am absolutely not saying that if they played infinite games, they'd win 8 out of 10.
No, you aren't talking about frequency at all.
Right. I am saying my personal internal confidence is calibrated to 80%,
Exactly.
meaning I would be theoretically willing to risk 4 of my own dollars to win $1 on an Arduino Arsenal victory.
Which is a huge shift. The Bayesian view liberates probability.
How so?
It allows you to assign a mathematical probability to literally anything. The weather in 2048, a one-off robot soccer match who will win a specific election next month.
Because it's just about belief.
Yes, but it introduces a variable that absolutely terrifies traditional scientists.
Subjectivity.
Precisely, because it relies entirely on the background knowledge of the observer.
Right. Because I might know that the star robot for Arduino Arsenal has a rusty servo motor, so I say the probability of them winning is only 40%. But you don't know about the rust. So you just look at their past win record and say the probability is 80%.
Which happens all the time in real life.
So we are looking at the exact same single event, assigning completely different probabilities, and under the Bayesian framework, we are both mathematically correct.
As long as you are both processing your specific sets of information logically and rationally, yes.
That is wild.
Your degree belief is 40%, mine is 80%, and this right here is what sparked the statistical holy wars.
I can imagine.
Ronald Fisher, who is one of the founding fathers of modern statistics, was a staunch frequentist.
Okay.
He looked at Bayesianism and called it an impenetrable jungle that would destroy scientific precision by letting human opinion poison the math.
The hostility was real.
Very real.
The text includes this incredible quote from the psychologist Paul Meehl firing back at the frequentists.
Oh, I know the one.
He said that blindly following frequentist rules turns a researcher into a potent but sterile intellectual rake who leaves in his merry path a long train of ravished maidens but no viable scientific offspring.
It is evocative, to say the least.
I mean, tell us how you really feel, Paul.
But he had a point. Meehl was arguing that hiding behind the illusion of infinite objective repetition often leads researchers to ignore context, common sense, and background knowledge.
Which leads to bad science.
Right, resulting in mathematically perfect studies that mean absolutely nothing in the real world.
It's just wild that so much drama is hiding behind these formulas.
It really is a soap opera.
But I guess the reassuring part of the source material is that despite this philosophical warfare, once you actually define what probability is, the rules of how it behaves are universally agreed upon.
Thankfully, yes. And to see those rules in action, we have to look at the space where outcomes actually happen.
Right. We have to define our sample spaces and our distributions.
Exactly. And the author of the text provides an incredibly mundane, yet perfect example to ground this.
The wardrobe. The famous pants distribution.
Yes!
I love how this just strips away all the intimidation factor of statistics. The author owns exactly 5 pairs of pants.
The simple life?
We labeled them X1 through X5. Blue jeans, gray jeans, black jeans, a black suit, and blue tracksuit pants.
Okay, so to speak the language of statistics here, picking one specific pair of those pants on a given morning, say, the black suit is called an elementary event.
An elementary event.
Yes, it is the smallest indivisible outcome. You can't wear half a suit. And the entire wardrobe, the complete collection of all 5 pairs, is called your sample space.
Got it. And every elementary event has a probability, a P of X, attached to it.
Right.
And the first rule is that this number has to be between 0 and 1. 0 means impossible. 1 means absolute certainty.
Perfect.
But the second rule, the law of total probability, is where the real structure forms, because the author always wears pants.
A baseline assumption we must make for public decency, obviously.
Yes, obviously. Because of that, the probabilities of all 5 pairs of pants must add up to exactly 1.
Because something in the sample space is mathematically guaranteed to happen.
Right. So let's say blue jeans are a 0.5 probability, gray jeans are 0.3, black jeans 0.1, the suit is 0 because he works from home, and the track suit is 0.1.
Okay.
If you add those up, you hit a perfect 1.0.
Exactly.
But the text points out, we don't just care about elementary events. We care about broader categories too.
We care about non-elementary events. Suppose you want to know the probability that the author wears jeans.
Okay.
Jeans is not a single item, right? It is a category encompassing the blue, gray, and black jeans.
Right.
To find that probability, you simply add the probabilities of the elementary events contained within that category.
So 0.5 plus 0.3 plus 0.1 gives us 0.9.
Exactly.
There is a 90% chance he wears jeans.
Oh,
That's intuitive enough.
very straightforward.
But this simple addition lets us derive much more complex rules, like conditional probability.
Yes, this is a crucial concept.
And the text has this brilliant scenario for this.
Yeah.
Yelling to a spouse in the other room.
It's a very practical example. Imagine the author gets dressed and yells out to his wife, "I'm wearing jeans today."
Okay.
The wife cannot see him, but she has just received a crucial piece of conditional information. The condition, jeans, has been met.
Right.
How does that reshape the entire probability landscape?
This was honestly a light bulb moment for me reading this. She knows he's wearing jeans. So instantly, the probability of the black suit and the blue tracksuit drops to absolute zero.
They're removed from reality.
Right, they just poof out of existence.
Yeah.
But the remaining probabilities, the blue, gray, and black jeans, still only add up to 0.9.
Which is a problem.
Yeah, because we just established the law of total probability. The remaining options must sum to 1, because he is definitely wearing something.
This is the critical insight right here. The relative likelihood between the remaining pairs of jeans hasn't changed.
What do you mean?
Well, before the announcement, he was 5 times more likely to wear blue jeans, which was 0.5, than black jeans, which was 0.1.
Right, 0.5 to 0.1 is a 5-to-1 ratio.
Exactly. That 5-to-1 ratio is a fundamental fact of his behavior, and it must be preserved in the new mathematical reality.
Oh, so to make them sum to 1 while keeping that exact 5-to-1 ratio, we just divide every remaining probability by the total probability of the condition that was met.
Precisely.
The condition was jeans, which had a probability of 0.9.
So you do the math.
Right, we take the blue jeans 0.5 and divide it by 0.9. We take the gray jeans 0.3 and divide by 0.9. And the black jeans 0.1 divided by 0.9.
And what happened?
Now, magically, they sum to a perfect one, but the internal ratios are completely identical.
You have just conceptually derived the formal equation for conditional probability without needing to memorize a single formula.
That feels like a superpower.
It is. The probability of event B that an event A is simply the probability of both happening divided by the probability of event A. It is just logic, cleanly mapped onto arithmetic.
Okay, so that's a custom-made, slightly silly distribution. But if you're taking a stats course, you're going to deal with standardized distributions.
You will see them everywhere.
The classic shapes that govern the universe. And the first one the text tackles is the binomial distribution.
Yes. Binomial distribution handles discrete, countable trials where there are only 2 possible outcomes: success or failure, heads or tails.
And the visual the text uses for this is rolling 26-sided dice.
A bit like a tabletop game.
Right. But instead of numbers, 5 sides are completely blank and 1 side is a skull printed on it.
Okay.
You roll all 20 dice at once. The binomial distribution is the math that tells you the exact probability of getting, say, exactly 4 skulls.
And it requires 3 pieces of information to do that. N, which is the number of trials, which here is 20 dice.
Right.
The probability of success on a single trial, which is 1 in 6 for the skull, and the specific outcome you want to measure, which is 4.
And if you map this out, you get a bar chart.
A very clear visual.
Picture a graph. Along the bottom x-axis, you have the numbers 0 through 20. Those are all the possible skull counts. Above each number is a bar representing how likely that outcome is. The bar over the number 4 is about 20% high.
Exactly.
But you don't just have to ask for exact numbers, right? Statistical software allows you to ask for cumulative probabilities.
It does. Instead of asking for the exact probability of 4 skulls, you might ask for the probability of rolling 4 skulls or fewer.
Oh, I see.
The software simply adds up the height of the bars for 0, 1, 2, 3, and 4 skulls.
Which gives you about 77%. And you can actually run that in reverse.
Yes, using functions like Quanum in R.
Right. You can ask the computer to find percentiles. You can say what number of skulls represents the 75th percentile.
But here's where discrete math gets a little weird.
Oh, yeah, the chunkiness.
Right. You can roll 3 skulls. You can roll 4 skulls. You cannot physically roll 3.8 skull.
No matter how hard you throw the dice.
Exactly. The binomial distribution is chunky. It is not smooth. If the exact 75th percentile mathematically falls somewhere in the empty void between 3 and 4, the software cannot give you a fraction of a skull.
So what does it do?
It rounds up to the nearest valid discrete outcome, which is 4.
Which is a perfect segue. Because while skulls and coin flips are chunky and discrete, the vast majority of the real world, the things we actually care about measuring, like height, weight, time, test scores, is completely smooth.
It is continuous.
It's continuous. And that requires us to upgrade from the chunky bar chart of the binomial distribution to literally the most important concept in the entire field, the normal distribution.
The bell curve. This is the cornerstone of everything that follows in statistics.
It really is.
Unlike the binomial distribution, which is defined by counting trials and successes, the normal distribution is entirely defined by just 2 parameters, the mean and the standard deviation.
The text uses Greek letters for these, which I know is where a lot of students start to panic.
They do, but they shouldn't.
Right. The mean is mu and the standard deviation is sigma. But if you just visualize them, they aren't scary at all.
So let's build that visualization for you. Imagine a perfect symmetrical bell curve sitting on a horizontal line.
Yeah.
The mean mu simply dictates where the absolute center of that bell curve is placed on the line.
So if I change the mean from 50 to 100, the shape of the bell doesn't change one bit. The entire perfectly shaped bell just slides 50 units to the right.
Precisely. The mean is just the location. The standard deviation, sigma, is the shape.
The shape.
It measures how tightly the data clusters around that center.
So if you have a tiny standard deviation, it means almost all your data is practically sitting right on top of the mean. So the bell curve gets incredibly tall and ultra skinny, like a needle.
Yes.
If you have a massive standard deviation, the data is scattered everywhere. The bell curve gets squished down flat like a really wide, shallow hill.
But here is the magical property of the normal distribution. Whether it looks like a tall needle or a wide hill, the internal proportions are universally identical.
Oh, the 68-95-99.7 rule.
That's the one.
I love this rule. If you measure the distance of one standard deviation out from the mean in both directions, exactly 68.3% of all your data will live inside that space.
Always. Always.
If you go 2 standard deviations out, you capture 95.4% of the data. 3 standard deviations out, you've captured 99.7%. It is just remarkably consistent.
It is deeply reliable. But moving from a discrete bar chart to a continuous smooth curve introduces a massive philosophical and mathematical paradox, one that routinely trips up students.
Oh, the exactness problem.
Yes.
Let me try to explain this the way the source material laid it out, because honestly, it totally broke my brain at first.
Go for it.
If you use a computer to ask for the exact probability of getting exactly 4 skulls, it gives you a normal percentage.
Right.
But if you ask a computer for the exact probability of pulling an observation of exactly 1 from a normal distribution, the software might spit out a number like 3.99.
Which should immediately terrify anyone who's paying attention 5 minutes ago.
Right, because the first rule of probability we discussed with the Pans distribution is that a probability absolutely cannot be greater than 1.
Exactly.
So what is the software doing? Why is it giving you 3.99?
Because it is not giving you a probability. It is giving you probability density.
Probability density.
Yes, because for a truly continuous variable, the probability of hitting one infinitely precise exact number is always unequivocally 0.
Consider the temperature outside right now.
Okay.
The app on your phone says it is 23 degrees, but it is not exactly 23.000000 degrees.
No, it never is.
It might be 23.01 or 22.9999984.
Right. The analogy that made this click for me from the text is throwing a dart at a dartboard.
Oh, I like that one.
Imagine the dartboard is a perfectly continuous space. What is the true probability that the absolute center of the tip of your dart hits one single, infinitely tiny geometric point?
A geometric point has 0 width, 0 height, and 0 area.
Exactly. You could throw darts for 1 billion years and never hit that exact microscopic coordinate.
Because a point has no area, it has no probability.
That is the key. Therefore, on a normal distribution graph, the vertical u-axis is not probability. The height of the curve is probability density.
It just shows you the relative concentration of outcomes.
Right.
So to find an actual probability, a number between 0 and 1 that means something, you can't ask for a single point. You have to ask for a range.
You have to draw boundaries.
You have to say, what is the probability the temperature is between 22.5 and 23.5 degrees.
Yes. And then you calculate the physical area trapped under the bell curve between those two boundary lines.
Because the total area under the entire bell curve from end to end is exactly 1.
Exactly. It requires a complete shift in how you view the numbers. You are no longer counting discrete events, you are measuring continuous areas.
Okay, so we've established the theoretical universe. We have our distributions, our bells, our densities. But here is the brutal reality of the text.
Okay.
In actual scientific research, you almost never have access to the full distribution.
Almost never.
You are basically fumbling around in the dark with a tiny fragment of reality. We have to talk about populations versus samples.
It is the defining struggle of empirical science. The population is the vast, complete group you actually want to make a claim about. All human beings, or every star in the galaxy.
Right.
The sample is the tragically small, finite set of data you actually manage to collect.
And the textbook uses a very clean example to start. A bag with 10 colored chips in it. 4 black, 6 white.
Okay.
That bag is our population. If I close my eyes, shake the bag violently, and pull out 4 chips, that is a simple random sample.
Because every single chip had an identical chance of ending up in your hand.
Right. And if you don't put the chips back after looking at them, that is sampling without replacement.
Yes.
If you record the color, toss it back, and shake the bag again, that is sampling with replacement.
Interestingly, pure statistical theory usually assumes sampling with replacement. It keeps the math cleaner. Even though in human trials, say, a psychology experiment, we rarely test the exact same person twice. We sample without replacement in reality.
But does that mess up the math?
The math shows that if the population is massive enough, the difference between the two becomes mathematically irrelevant.
Okay, that's a relief. But let's be honest, single random sampling is a fairy tale in most fields.
It truly is.
If I want to study human working memory, my population is all living humans. I cannot put 8 billion people in a giant bag, shake it, and pull out 100 randomly.
You definitely cannot.
I'm going to end up testing the people who happen to live near my laboratory.
Which means researchers are almost entirely reliant on biased samples.
Which sounds bad.
It can be, but the text details several workarounds. Stratified sampling, for instance.
Like that.
Well, if you were studying schizophrenia, pulling a purely random sample of 1,000 people might yield 0 actual patients because the condition is rare. So researchers intentionally divide the population into strata and oversample the schizophrenic population to ensure they have enough statistical power to actually measure something.
Well, that makes sense. Or there's snowball sampling, which I thought was brilliantly pragmatic.
Very useful in sociology.
Yeah, if you need to study a hidden population like undocumented workers or a heavily stigmatized group, you can't just run a random phone poll.
No, they won't answer.
Exactly. You find one person, build trust, survey them, and then ask them to recruit 2 of their friends. The sample snowballs through social networks.
It is wildly non-random, but it's the only way the data gets collected at all.
But the most common and most criticized method mentioned is convenience sampling.
Yes, the staple of modern research.
This is where researchers simply grab the data that is easiest and cheapest to acquire.
Which, in the field of psychology, basically means rounding up a bunch of 19-year-old undergraduate students who desperately need course credit and making them take your survey.
Seriously. If practically all of foundational psychology is based on a convenience sample of Western middle-class undergrads, shouldn't we just throw the whole discipline in the garbage? Like, how could we trust any of it?
It's very tempting to be cynical about that, but the text provides a vital framework for critical thinking here.
Okay, save psychology for me.
A biased sample is only scientifically fatal if the specific bias interacts with the specific phenomenon you are studying.
Okay, walk me through that. What does an interaction actually look like?
The source material offers a great comparison. Imagine 2 researchers studying working memory capacity.
Okay.
Researcher A somehow pulls a random sample of the entire globe, but only selects people born on a Monday.
Weird, but okay.
Researcher B pulls a sample consisting entirely of people living in Australia. Both samples are highly biased. Which study is more compromised?
Well, being born on a Monday is super weird, but being Australian is a very specific socioeconomic demographic. So the Australian one is worse.
You have to look at the interaction.
Oh, right.
Does being born on a Monday have any physiological, psychological, or sociological link to how working memory actually functions?
Almost certainly not.
Right. The bias is massive, but it is completely irrelevant to the phenomenon being measured.
Oh, but being Australian, That means you grew up in a specific industrialized education system. You were explicitly trained to take standardized tests a certain way. You might have cultural habits around focus and attention.
Exactly.
That demographic bias could directly, artificially inflate or deflate a working memory test.
You've got it. The lesson is that you cannot just point at a study, yell, "Your sample is biased," and dismiss the findings outright.
You have to do the work.
Yes, as a critical consumer of statistics, you have to do the intellectual work of explaining how that specific demographic quirk distorts the specific measurement being taken.
That completely changes how I read science journalism from now on.
It's a game changer.
Now, before we tackle the hardest part of the text, we have to lock down the vocabulary. Statisticians use entirely different alphabets to talk about populations and samples, right?
Yes, they do. And it is crucial to keep them straight if you're taking a course.
Right.
When we are talking about the massive, unknown, true population, we use parameters. Parameters are represented by Greek letters.
Like mu and sigma.
Exactly. The true population mean is mu. The true population standard deviation is sigma.
And when we are talking about our tiny, messy, concrete sample, we use statistics.
Yes.
Statistics are represented by standard Roman letters. The sample mean is X bar, the sample standard deviation is just an S.
The parameter is the hidden truth we are hunting for. The statistic is the flashlight we're using to look for it.
I love that analogy.
Right.
Which brings us to the absolute climax of this entire deep dive.
The big leap.
If our samples are small, messy, and fundamentally biased, how on earth do we bridge the gap?
It seems impossible.
It does. How do we use X bar to make a mathematically rigorous claim about mu? If we don't have the whole picture, how do we know our guess isn't just a random hallucination? We need a mathematical miracle.
Well, the text actually provides two miracles, and they are the pillars of modern science.
Okay, hit me.
The first is the law of large numbers.
Ah, right. The text introduces this with a quote from Jacob Bernoulli back in 1713.
A classic.
He wrote that even the most stupid of men, by some instinct of nature, knows that the more observations you make, the less danger you have of wandering away from the truth.
It is a universal human intuition, expressed a bit rudely maybe,
Just a bit.
but a computer simulation proves him completely right. The source text simulates measuring IQ scores.
Okay.
Let us assume God comes down and tells us the true population mean IQ of the universe is exactly 100.
But we as researchers don't know that yet.
Right. So we take a sample of 100 people, we calculate our sample mean, our X bar, and it comes out to 98.5.
It's close-ish, but it's fundamentally wrong.
However, if you increase your sample size to 10,000 people, the sheer weight of the data begins to crush the random variation.
Because the extremes balance out.
Yes. The extreme highs and extreme lows cancel each other out. The sample mean of those 10,000 people comes out to 99.9.
Oh, wow. So the law of large numbers mathematically guarantees that as your sample size, your n, stretches toward infinity, your sample mean will flawlessly converge on the true population mean.
Exactly.
It's a very comforting thought.
It is conceptually comforting, but practically speaking, it is almost entirely useless.
Great. Really?
As the famous economist John Maynard Keynes observed, in the long run, we are all dead.
Brutal but true.
We don't have infinite time or infinite funding. We run experiments with 50 rats or 200 surveyed voters. A guarantee of truth at infinity doesn't help me know if my specific sample of 200 people is anywhere close to the truth right now.
Which brings us to the second, much more powerful miracle.
Yes.
It has a terrifying name. The sampling distribution of the sample mean.
It is a mouthful.
Even saying it out loud makes my head spin. It uses sample and distribution right next to each other.
Yeah.
But the text visualizes this in a way that actually makes it intuitive.
Let's walk through it.
Okay, imagine a population distribution that is completely flat. Just a uniform rectangular block.
No bell curve in sight.
Right. It represents the numbers 1 through 10, and every single number is equally likely to be picked. The true mean of this perfectly flat population is 5.5.
A perfectly flat reality.
Now, I conduct an experiment. I take a random sample of 20 numbers from that flat population.
Okay.
Because of pure random luck, my sample happens to grab a few extra 9s and 10s. So I calculate the mean of my specific sample, and it's 6.2.
That is one sample mean.
I write 6.2 on a sticky note and put it on the wall.
Okay.
Then I do again. I pull another 20 numbers. This time, I get unlucky and grab a bunch of 2s. The mean of this second sample is 4.8.
Another sample mean.
I write it on a sticky note. I repeat this agonizing process 10,000 times.
That's a lot of sticky notes.
I now have a wall covered in 10,000 sticky notes, each containing the mean of a different small sample.
And here's the question that unlocks the universe.
Yeah.
What happens if you take those 10,000 sticky notes and stack them up into a histogram? What physical shape do they form?
This is the part that feels like actual magic to me.
It really does.
The original population was a flat, featureless block. But when I stack up the means of all those samples, they arrange themselves into a flawless, perfectly symmetrical bell curve,
A normal distribution.
peaking exactly at 5.5.
You have just practically constructed the central limit theorem.
But why does it do that? Why does a flat block turn into a bell just because I took averages?
Think about the physical mechanics of an average. To get a sample mean of 10, you would have to randomly pull 20 tens in a row from that block.
The odds of that happening by pure chance are astronomically low.
Exactly. To get a sample mean of 5.5, you just need a normal mix of highs and lows that balance each other out, which is highly probable.
Oh, I see.
Therefore, the vast majority of your sample means will cluster tightly around the true middle, creating the massive peak of the bell curve, with very few extreme sample means tapering off into the tails.
It's an inescapable law of nature. It just forces order out of total chaos.
It does.
The central limit theorem dictates that no matter how bizarre, skewed, or flat your original population is, the distribution of your sample means will always be a normal bell curve.
Always. And because it is always a normal curve, it grants us two massive mathematical gifts.
Okay, what are they?
First, the absolute peak of this new curve is exactly the true population mean.
Now,
Second, the width of this curve, the standard deviation of the sample means, has a special name. It is called the standard error.
standard error. That phrase is literally everywhere in scientific papers.
Everywhere.
So standard error isn't measuring how spread out my raw data is. It's measuring how much I can expect my sample mean to wildly bounce away from the true population mean due to random sampling luck.
You've got it exactly. And
Yeah.
the standard error shrinks as your sample size grows.
Makes sense.
If you only sample 5 people, your sample means will bounce around wildly.
Yeah.
Your standard error is huge, meaning your bell curve is flat and wide. You have very little certainty. But if you sample 1,000 people, the averages barely move. Your standard error is tiny. Your bell curve is incredibly tall and narrow, precisely pinpointing the truth.
And because we know the sampling distribution is guaranteed to be a normal curve, we get to use the cheat codes we learned earlier. The 68, 95, 99.7 rule applies here too.
Yes, it does. We can standardize this curve of uncertainty using z-scores.
Z-scores, right.
A z-score is simply a way of creating a universal ruler. Instead of talking about raw numbers, like saying, my sample mean was 4 units away, you translate it into standard deviations.
What's the formula for that?
It's simply your raw score minus the mean divided by the standard deviation.
So if I calculate a z-score and it comes out to exactly 1, that instantly tells me my sample mean is exactly 1 standard deviation above the true center.
Yes.
And because of the normal curve rules, I instantly know exactly how rare or common that kind of bounce is.
The central limit theorem and z-scores provide the absolute scaffolding for everything. We are finally equipped to do what the text promises in Section 6, estimation.
We are ready to make inferences.
Finally.
The leap from the sample to the population. And the text points out that we do this for 2 very different reasons. Concrete estimation and abstract estimation.
Yes. Concrete estimation is basically a matter of logistical survival.
Like the shoe company example.
Right. If you are the CEO of a shoe company, you desperately need to know the true population distribution of human foot sizes.
Because if you guess wrong, you manufacture millions of size 14 shoes that nobody buys, and you go bankrupt.
Exactly. So you take a massive sample, calculate the sample mean and standard deviation of physical feet, and use those to estimate the true parameters to set your factory machines.
But the text notes that in fields like psychology or sociology, things are notoriously abstract. We aren't measuring physical feet.
No, we're measuring constructs.
We are asking people to fill out a questionnaire rating their happiness on a scale from 1 to 7.
Which is fraught with existential peril, honestly.
I can imagine.
Does a singular objective population of human happiness even exist to be measured?
That's deep.
When you ask someone to circle a number, are you measuring their internal joy? Or are you just measuring their cultural bias toward answering surveys moderately?
Oh, that's a great point.
Some people will literally never circle a 7 because they think claiming perfection is arrogant. Some will only circle 1s and 7s because they are dramatic.
So if the data is that murky and subjective, why do psychologists even bother crunching the numbers?
Because of the power of experimental design. In psychology, the goal is rarely to find the absolute true mean of global happiness. Who actually cares if the global average is 4.2 or 4.6?
True.
The real goal is to discover causality. Does variable X cause a change in variable Y?
Ah. So we don't care about the absolute number, we just care about the difference between numbers.
Precisely. You take a large sample of people and measure their baseline happiness. Then you administer a treatment. Maybe you give them all a piece of chocolate.
I'd volunteer for that study.
Me too. Then you measure their happiness again. Now you have 2 sample means.
And thanks to the central limit theorem and the standard error, we know mathematically exactly how much 2 sample means should differ just based on random natural bouncing around.
You have nailed the core logic of all scientific testing right there.
Wow.
If the difference in happiness between the chocolate group and the baseline group is significantly larger than the natural variation predicted by the standard error, then it is mathematically highly improbable that the difference was just luck.
So you can confidently claim that the chocolate caused the change.
Exactly. We use the predictable mathematics of random chance to isolate the hidden signals of our experiment.
It's brilliant. But to do that accurately, our measurements of the variation have to be flawless.
They do.
Which brings up a very weird mathematical hiccup in the text about biased estimators.
Yes, the problem of estimating standard deviation.
Right. So if I want to guess the true population mean, I just use my sample mean. The sample mean is an unbiased estimator.
Correct.
It doesn't systematically cheat. It doesn't aim artificially high or low. On average, it hits the target. But let me guess. If I want to estimate the true population's variation, I can't just use my sample's variation.
Your guess is correct, and it frustrates absolutely every student who encounters it.
Why?
The sample standard deviation is a biased estimator. It is systematically flawed. It consistently, reliably underestimates the true variation in the population.
Okay, the text uses a highly ridiculous example to illustrate why this happens. It proposes measuring the cromulence of shoes.
A completely meaningless metric.
Yeah, totally made up.
Yeah.
But structurally perfect for the explanation.
Exactly.
So imagine I take a sample of exactly one shoe. My N is 1. I measure its cromulence, and the score is 20.
Okay.
What is the mean of my sample? Well, it's 20.
Right.
But what is the variation of my sample? Well, it's just one number. It doesn't vary from anything. So my sample standard deviation is exactly 0.
Now imagine using that sample statistic to estimate the population parameter. You would be officially estimating that the true variation of all shoes in the universe is 0. Meaning, you are mathematically claiming every single shoe in existence has a cromulence of exactly 20.
Which is clearly absurd.
Right, because a sample size of 1 simply hasn't been given the opportunity to see any variation.
That makes sense. But what if I sample 2 shoes? Say I get a 20 and a 22. Now I have a little bit of spread.
You do.
But the text explains that mathematically, my sample variance relies on something called the sum of squared deviations.
Yes.
We have to break that jargon down. What does that actually mean?
It is much simpler than it sounds. Take your sample mean, in this case, 21.
Okay.
For every data point, you measure how far it deviates from that mean. The 20 is negative 1 unit away. The 22 is positive 1 unit away.
Got it.
You square those distances to get rid of the negative signs, and you add them all up. That sum of squared deviations is the raw material of your variance.
But here is the core issue of why small samples underestimate the population.
Yep.
In a massive population, extreme values, the massive outliers, are naturally rare. Most of the population clusters near the middle.
Right.
So when you pull a tiny sample, odds are overwhelming that you are only pulling normal, middle-of-the-road numbers. You almost certainly miss the extreme highs and extreme lows that create the true massive width of the population's variation.
That is exactly it. Because your tiny sample naturally clumps together, the distances from the mean are artificially small. Therefore, your sum of squared deviations is artificially small. If you run a computer simulation of thousands of small samples, you will see the sample standard deviation consistently, systematically guessing too low.
It is biased.
It is.
So we have a broken tool. How do statisticians fix it?
They apply a mathematically elegant patch called Bessel's correction.
Bessel's correction.
Normally, to find the variance, you take that sum of squared deviations and divide it by n. your total number of observations. To fix the bias, you simply divide it by n minus 1.
Wait, that's the whole fix. Just subtract 1 from the denominator.
That is it. Think about the arithmetic. If you divide a pizza into 9 slices instead of 10, the slices are slightly bigger, right?
Right.
By dividing by a slightly smaller number, n minus 1, you artificially inflate the final result.
Oh.
You inflate it just enough to perfectly counterbalance the fact that small samples naturally underestimate the spread. This corrected formula gives you sigma hat, the unbiased estimate of the population's standard deviation.
It's just a mathematical cheat code to artificially bump up our guess.
Basically, yes.
And most software, like R, does this n-1 correction completely invisibly in the background, which is great, but also why it's so important to know what the machine is actually doing.
You have to know the mechanics.
Okay, we have reached the summit. We have our unbiased estimates. We know our standard errors. But the text hits us with this really sobering quote. Statistics means never having to say you're certain.
The entire journey has been about quantifying our ignorance. We can never offer a single exact number and claim it is the absolute truth.
A point estimate is fragile. It's almost guaranteed to be slightly wrong.
Exactly.
We don't want a point. We want a fortress. We want a confidence interval.
The confidence interval is the masterstroke of inferential statistics. It takes your sample mean, your standard error, and the rules of the normal curve, and combines them to draw a mathematical perimeter around the truth.
So let's build a 95% confidence interval. We established earlier with the 68, 95, 99.7 rule that 95% of all outcomes in a normal distribution fall within about 2 standard deviations of the center.
Right. To be exact, and to please the grading software in your course, the text notes the precise multiplier is 1.96 standard deviations.
1.96, okay. So the construction is simple. You take your sample mean, that's the anchor right in the center.
Okay.
Then you calculate your standard error, which, remember, is the standard deviation of how much your means bounce around.
Yes.
You take that standard error and multiply it by 1.96. You add that chunk to your mean to set your ceiling. You subtract that chunk from your mean to set your floor.
You have just constructed a boundary, a mathematical net.
And we can stand there and declare, we are 95% confident that the true population mean lives somewhere inside this net.
It's a powerful statement.
And if we want to be 99% confident, we just swap out the 1.96 for a bigger multiplier, which makes the net wider.
Exactly. We cast a wider net. We are more certain to catch the truth, but our estimate gets less precise.
There is, however, one final agonizing wrinkle the text introduces regarding confidence intervals, and it relates directly to our n-1 cheat code. Because we didn't actually know the population's standard deviation. We had to use our sigma hat to guess it.
Exactly. Because we used an estimate to build our standard error, we injected a tiny bit of extra uncertainty into the entire system. Our math is slightly less reliable.
Right.
Because of that extra uncertainty, it is no longer mathematically legal to use the perfect, pristine, normal distribution to find our 1.96 multiplier.
So what do we use instead?
We use the t-distribution.
The t-distribution. The text talks about this, but I couldn't really visualize it. How is it different from the bell curve?
Imagine a standard, normal bell curve made out of clay.
Okay, a clay bell.
The t-distribution is what happens if you put your hand on the top of that bell and press down slightly. The peak gets squatter and lower, and the clay you push down oozes out into the edges.
Oh, I see.
The tails of the curve get fatter and thicker.
Squatter peak, fatter tails. What does that physically mean for the math, though?
Fatter tails mean that extreme, unexpected outcomes are slightly more probable than they would be under a perfect normal curve. It is the math physically accommodating for your ignorance.
Wow.
Because the t-distribution has fatter tails, you have to go further out to capture 95% of the area. So instead of a multiplier of 1.96, the t-distribution might force you to use a multiplier of 2.05 or 2.1, depending on your sample size.
Which naturally makes your confidence interval wider. The math punishes you for not knowing the true standard deviation by forcing you to cast a wider, vaguer net to maintain your 95% confidence.
It is a built-in penalty for uncertainty.
That is incredible.
It is profound mathematical humility. It protects the absolute integrity of the scientific claim.
What an absolute marathon this has been.
Yeah.
Let's just trace the arc of what we just covered. We started by debating the philosophy of a coin flip, realizing that probability can be an infinite physical frequency or a deeply personal subjective belief.
The philosophical bloodbath.
We opened up the wardrobe to see how sample spaces dictate the rigid rules of addition and conditional logic.
We realized that continuous data requires us to measure the area under a curve because hitting an exact point on a dartboard is practically impossible.
We confronted the brutal reality that our samples are almost always biased, but learned that we only need to panic if that bias directly interacts with what we are specifically measuring.
And then the miracles.
Yes, the central limit theorem, transforming chaotic, flat populations into predictable, majestic normal curves just by taking averages.
And finally, we use that predictable curve along with the humbling, squished shape of the t-distribution to build a confidence interval, a precisely measured net that traps the hidden truth of the population.
We evolved from just collecting stamps and reading the data we have to wielding the inferential power to understand the data we will never see.
It is the closest thing to clairvoyance that humanity has ever invented.
But to leave you with one final, provocative thought as you take this back to your course, let's return to John Maynard Keynes. In the long run, we are all dead.
The law of large numbers offers us the comfort of absolute truth at infinity. But we don't live at infinity. We live our lives in the chaotic, messy, small sample reality of the present day.
And our present day is relentlessly bombarded with statistics. The next time you open the paper and see a political poll claiming exactly 23%, or a flashy study stating a new drug improves focus by exactly 14%, pause.
Ask yourself a question.
Ask yourself, are they trying to sell me a point estimate, or do they actually provide the confidence interval? Because the point estimate is an illusion of exactness designed to make a good headline. It is almost certainly wrong.
The absolute truth of reality does not live in the exact number. The truth lives in the precisely measured space of our own uncertainty.
So demand the interval, demand the boundaries of their ignorance. Thank you so much for joining us on this massive journey on the deep dive. Whether you are using this to ace your stats exam or just to navigate the headlines a little more clearly, take these mental models with you. Stay curious, question the sample, and we will see you next time.